Now we should be recording. Okay, so welcome to the fifth lecture on NLP with deep learning. So today we are gonna go deeper in both terms, like content-wise, and also deeper in terms of neural networks. So finally, we're going to leave our simple network, which was the log linear model with basically a single layer function, so to say, and we've moved to something which is called feed-forward network or multi-layer perceptron or deep neural net. And we will be talking about language modeling, which is a crucial part of contemporary NLP. So these are the topics. After today, you should be able to, build a classifier for multiple classes, so not just a binary one, and understand what actual language modeling is and why is it really crucial. And when we talk about large language models, what this could really mean. Okay, so let's do this in next 90 minutes. So let's start first with where we finished last time, which is the binary task. So what was the we're dealing with what was it? Movie reviews, right? Binary, positive or negative. This is the task we were doing last time, right? Is it true? Okay, good. So, and it was kind of limited model because we had just like two outputs, so either yes or no or 0 or 1, and it's kind of would be. We might have problems, for example, which need multiple classes. So, for example, if you recall from the first lecture when we talked about NLP tasks, we had one of the tasks was SNLI, so Stanford Natural Language Inference data set, where you had two sentences, and the task is about to decide whether these two sentences are inference, contradicting, or neutral. So we are basically two classes. There are tasks where you might have multiple classes, for example, classifying documents into different classes, like topic-wise. Is it politics, sports, blah, blah, blah. You might have basically 50 classes. And there could be tasks which have even like 50,000 classes, as we'll see later. So this is what we need to really model. Okay, so binary, easy and simple to start with, but in reality, we might have multiple classes to classify our texts. Good, so this is just for recalling what we were talking last time about, is that our binary text classification function. So just to remind you of what we are, how we're kind of draw these graphs. So this is a computational graph where we have our inputs. What was the input for our binary classification task? So what did we plug in? How did we model text? Anybody remembers how we turn text into a vector of numbers? Was there something particular we used? Yeah. Yeah, we tokenize the text, of course, so then we have a bunch of tokens. So how do you turn a bunch of tokens into a vector? The back thing. Okay, so does the back thing has a name? One-hot encoding of words. Okay, so each word has basically a vector of dimensionality of what? So how much words we have? Back of words is the word. How much words we have is corresponding to what? But how do we know how many words we have? So how did we solve it? You don't know exactly, okay?
For dictionary.
We have a dictionary. Okay, so we build a vocabulary, and this is how many words we have. And we said each word corresponds to one position in this dictionary. And this will be one-hot encoding. And somebody said back of words, so we basically treat each word as a vector, and we just made the average of all vectors, all words in our input. So this is back of words. Okay, so learn this. So this is our input here. And then so this is a vector, and we are multiplying this or projecting this into another sort of space, one-dimensional space. So here, what comes out was just a real number. And this was our sigmoid function, which squeezes everything into between 0 and 1. And this was our loss function. So the loss function was looking what's the What's the sort of difference? So how wrong are we on this particular example? So what's the difference between the gold standard label and the predicted label from the network? So which loss did we use, by the way? We had a couple of losses. What is the loss that, the basic default loss? Anybody remembers? Okay, so this is the cross-entropy loss, binary cross-entropy. This is what you're saying or something else? Yeah, but we're not using mean square. I mean, mean square you can use, I mean, of course, it's a valid one, but basically you would typically, as a rule of thumb, just use cross-entropy here. Okay, so we have cross-entropy. Cool. So now we should be on the same page, although you forgot or don't remember exactly. Now we should be, on the same starting page. So this was our binary model. And we need to turn this into predicting, well, more things. Not just a single real number, but something else. So how we turn from binary to multi-class labels? Well, so far we mapped the gold label into 0 or 1. But if we have, for example, we want to classify, we get a document that the task is to classify it into languages. So for example, our set of languages, well, is very limited. We have only 6 languages in our task, but why not? So English, French, German, Italian, Spanish, and other. And given a text, we want to classify this text into one of those languages based on some features, words, whatever, characters. So how do you think we can now label the gold label? How can we model the gold label right now if we have different categories? Because there's no ordering of these things. So it wouldn't make sense to say English will be 0, French 1, German 2, and so on. I mean, you would put some ordering into that, so it makes no sense. So is there any other solution? What can we do about it? I'm not talking, yeah, I mean, you're talking about output layer, but I'm just thinking about the gold label. The output layer is how you model it, but you can model it like regardless of neural networks. How would you turn your categorical labels into something meaningful mathematically? Yes. So like that, this would be like English vector. So does it have a name, do you think? It's one-hot encoding, exactly. So in the same spirit as we turn our categorical words into vectors, which words also have no ordering. So we just said like, well, they will be somewhere ones and somewhere zeros. We just turn this into one-hot encoding of labels. So basically, exactly as you said, like we could turn this into English at position 1, French at position 2, and German position 3, and so on. And the dimensionality is the number of classes, which is the out here. So this would be 6, vector of size 6. This is arbitrary. I mean, we could turn it other way around because there's no ordering. So it could be as we decide in the task. Okay, does it make sense? Okay, cool. So now we solve the multi-class labels. This is great. Now let's turn back to our model. So how can we solve this with our simple model for binary classification? Well, we're gonna use again the input vector and the projection, and we might actually say, yeah, well, for each language, we might have a weight vector and a bias. So we can take the input and multiply by doing the linear projection by this W and B, so this projecting into another space. And for each languages, the projection would be different. Well, we can do this. And then once we do this projection, we can take that, we can say that the language which is going to be predicted is the one with the highest score. I mean, here we kind of still don't use the sigmoid function, but well, maybe you just want to have a high score here. So what we are actually doing that, in a way, we can rearrange this per language weights and biases into multiplying the input by a vector, and the vector would have the dimensionality of, like, what would be in? So the size of the input vector times, so this is the number of columns, times 6, which is the number of languages we have. And then the question would be, what is the dimensionality of this bias? It's again a vector of number 6. So what does it mean? Maybe I should draw an example. So this is our input vector, x. And then we would multiply it with a matrix W. So this is our W. And the dimensionality of that is, I don't know, what's the dimensionality of the vocabulary, roughly? What is that? Well, how many words we have in English, say, or in a language? Yeah. Say again?
I mean, we have more, but maybe 5,000 for simple classification, and maybe you want to go like 30,000 if you want.
You can go crazy, so let's say 50,000. Okay. I mean, whatever, something like that. So 100,000. Let's say it's 50,000. Why not? So here's a 50K. So this is this is back of words 50K dimensionality. And then we multiply it by the matrix. So what's the number of rows here in this W matrix? How many rows do we have to have in this matrix? So it works, yes. 50K, exactly. Why? Because of linear algebra. You cannot multiply, you have to know the rules of multiplying 50K. And we said the number of columns is gonna be the number of languages, right? So this is our 6. And then, so what's going out of this is, what are we getting here? If you multiply this vector by a matrix, what are we getting out of this? I see you. I want to see somebody else. Like, what are we getting? I mean, it's linear algebra. Come on. Yes. You in the back, yeah. Oh, yes.
Vector of length.
Yes. Why? Because it's how linear algebra works. Okay, so yeah, exactly. We're getting a vector of length 6. Is it correct? I guess so. Yes, 6. Right? You multiply this by this, then this by this. So 6 times, and then you get a vector of length 6. Okay, so refresh linear algebra. I mean, multiplying vector by a matrix, you should know. Like, if I wake you up at the, in the middle of the night, you should know how to multiply this. So we get a vector, and then what did we say? We add a bias. So this is also the bias is number 6. So we get a vector of 6, and there will be some numbers. Okay, so we are using this projection. We're projecting our input vector of, what is this, like 50,000 into a vector of 6. And this vector of 6 is telling us something about what kind of, well, I would say it's like strength of association with this particular document with the language, but we will turn it, so these will be real numbers, but we will turn it into something even better for classification right now. So, any questions? Everybody's happy with multiplying a vector by a matrix. Okay, you make it your friend. Good. I think this is what we exactly did, right? Just now. So yeah, this is basically the high-dimensional linear function when we multiply a vector by a matrix, what we're getting out of here. So this is a linear projection. Okay. So we projected the input x to a output vector y, which is some lower dimension, basically number of categories. And we can pick the element of y hat with the highest value. And we could say, well, this is a prediction. And well, no, this is going to be, okay, excuse me. If we say this is the maximum argument of these vectors, so let's say we project it into vector of 0.1, minus 22, 67, and so on. So these will be of length 6. If we say the maximum argument will be maybe this, so this is position 1, 2, and 3. So then we would say, well, this is the position of the highest of the highest value in the vector. Okay, so this would be our y hat. There is a difference. So this y hat is a vector, and this y hat is just the index. But basically, we'll be mostly using just the vector of prediction, so the y hat vault as a vector. So as I just said, like the index of what is y hat is the index of the 1 in the 1. Oh, this is not a 1 hot. No, we don't have a 1 hot. Sorry, forget it, because we're having just the real numbers here. So this would be this example I just mentioned here. Anyway, So now we can turn so we have a function which maps our high-dimensional inputs to some 6 categories. And we want to actually turn this into something even better than just real numbers. I think we'll get to this in a couple of slides, but now we need to talk about representation. So what we are doing by learning or by doing this linear projection. And this is basically representations. So again, we have a function here, which is a linear map from our input document, which is back of words. Then we map it to some low-dimensional space, typically, and add some bias. So this is a document representation, and this is a back of words we were just talking about, right? No, so just the dimensionality is the size of the vocabulary. So in a way, the X does represent the document, right? It's not words anymore. It's just a vector. There's mostly zeros because if you have a sentence of length 6, for example, or length 5, then in your vector, back of words, it will be mostly zeros, and maybe at 5 positions, this will be some number because you have 5 words. It could be even less. If this is like 5 repetitive words, your back of words would be just all of zeros, and there will be 1 position which is filled with some numbers. So, but this is a document representation. It represents the document basically in the vocabulary space, if you will. At the same time, when we project it into something else, now into this smaller vector, maybe of size 6, it's actually also a document representation. It still represents the document, but the representation is now more specialized for the language prediction task. We project it from one space to another space, and these have different properties. The first space looks more, the back of word space, the 50,000 vector, looks more, I would say, generic, because you can use it for, I don't know, you can project it into size of 6, size of 1, whatever. While when we project it into using our W, and we don't know where the W comes from yet, but let's say it's a projection into some smaller space of 6 languages, then we just represent our document in the space of 6, which is now very specialized for the language prediction task, because we have these 6 different categories corresponding to languages, but it still does represent the document, right? So we just project it, or not learn, but we just turn one representation of the document into another representation of the document using just a linear transformation. Okay, so this is the conceptual thing. Somehow you can conceptual way of looking into these linear projections, turning from one space to another space. And these are not really equivalent, but they have different properties which might be useful for one or the other task. So, and of course, this W, as you might remember, and bias, these are parameters which we are going to learn. So these are learnable parameters. So we can learn how to project from one space to another space. We can learn how to project from one representation to another representation. So we are learning representations of a document. So this projection will be learned. This is trainable. Which means this learned representation is actually centered to deep learning, because we'll be using these linear functions and some nonlinearities everywhere in our network. So there will be lots of projections from one representation to another representation. And these representations are learned from data. And by learning these representations, basically the model trains or learns, and this is crucial to deep learning. Okay, so well, one can argue this is the main power of deep learning, is the ability to learn good representations. So we'll see it in the deeper model. There will be some representations somewhere in the network that we don't really know what they are, but they can be learned in a way that actually work for the task better than having just one representation to another representation. Okay, it was a little bit abstract now, but I hope you get a gist. Like, representation is crucial. One space, another space, and the transformation from one to the other is learned from data. And mostly this transformation is useful for solving the task. Okay, so we have a representation. Any questions? Okay. So now let's go back to to this problem. I mean, we had, what did we have? We have a bunch of numbers, and maybe we wanna turn it into something better for actual prediction, because our gold labels, our y, is some one hot. So something like 0, 1, 0, 0, 0, 0. And what's coming out of our function is a bunch of numbers. So we had a function which turned a real number into a probability, right? What was that? Any real number turning into something between 0 and 1. We have a sigmoid function, exactly. So the sigmoid turned a number into probability. Well, we want to do something similar for a bunch of numbers, so for a vector. So this brings us to how to turn output vector into probabilities of classes. So recap. Okay, what is recap? Categorical random variable x is defined over k categories, typically mapped to natural numbers 1 to k. Okay. Each category parameterized with probability, so probability of being k. I mean, of course. I mean, this is a probability distribution over categories. And to be a probability distribution, it has to sum up to 1. Which means, okay, if I have a bunch of numbers here, let's say 3 numbers, 0, 0.1, 0.8, and 0.1. This looks like a probability distribution over three classes. Sums up to 1, right? Is it like 1, 0.1, 0.8, 0.1? It sums up to 1. Good. These are all between 0 and 1. So these are valid probabilities. And what else? That's it. That's all I need. They have to sum up to 1. So if we have, for example, 6, classes, so again, English, what was that? French, German, and so on, we could have the same vector of numbers, and then the probability distribution over these classes could be like, I don't know, 0.1, maybe 0, 0, 0.8, 0, 0.1. I hope it sums up to 1. Yes, it does. So this is a probability distribution over our categories. Okay? Any questions? That's great. Okay, so this sounds like a common sense, but I just want to highlight this example. Okay, so this is what we might want. Yes, you have a question. How I turn what into probabilities? Yeah, that's a question. That's what we're going to solve. I mean, now we know what we want to have, and we haven't talked about how to get there. So, but it's yeah, that's the question we're going to address. How to turn, this is your question, by the way, how to turn unbounded vector in, k real numbers into categorical probability distribution. Okay, so we had a sigmoid for just one number. So sigmoid, how is a sigmoid? It's 1 over 1 plus a minus 2 to the power of minus x. So maybe, in our solution to this problem, there will be some exponentiation as well. And, well, turns out that we have this beautiful function called Softmax. And what we are going to do, so let's just have a look what is Softmax is doing. Okay, so element-wise, for each element xi, okay, so if I have 3 elements, I don't know, 0, no, let's just some numbers like minus 22, minus 400, and plus 20. Like, I mean, this could be a real value vector. Could be negative, positive, whatever. We don't care. And we want, by the way, can you read this? I mean, it's horrible writing. I'm sorry. So this is a minus 22 plus 400 and something. These don't matter, but just, as an example. So what we're going to do is we going to iterate basically over all these positions. So I is going to be, so k in this example is 3. And for each of these positions, we're first turning this into what? What's gonna this exponentiation do? You have a real number, could be anything, and you exponentiate it. What is it going to be? Yes, you. Yeah. It's gonna be always positive. Okay? Another property of exponentiation? What's exponent function doing? There's a great property, yes.
It's never zero.
Well, yeah, okay, it's never zero, yeah. Okay, so it's like, will be like this. This will be the range of x. But there's another property of exponentiation. Yes. Yeah, I don't think it matters here. That's true. That's true. It's 1 at 0, but there's another property. Yes. The derivative, we have a cool derivative. Okay, that's a nice property. Yeah, but anything else you were saying? It's monotonic. Exactly. What does it mean, monotonic? It's always raising, which means there's a mapping from all real numbers to positive numbers, which means the lower number here will be, so if you have two numbers, one is smaller, the other is greater, then after exponentiation, it will still be smaller and greater. Okay? So this is great. I mean, there's no bumps in there in the exponentiation. It will just basically turn everything into 0 and infinity, but it will be monotonic. So there will be this relation in there. Okay? Why is it important? Well, yeah, because I mean, if we have small number here and much smaller number here, we want to keep this, the ratio, not the ratio, but the relation between these two. So this should be still smaller than this one. Okay? Okay, so we're going to turn this into positive numbers. So it's going to be something like, I have no idea what, something 0. No idea. 0. Maybe 2, maybe 0.01, and plus 20. Whoa, it's going to be a huge number. Huge number. Okay, so we turn this into vector of positive numbers, but it's not a probability distribution. It's just some positive numbers. What is the solution to turn this that it sums up to 1? How do you make this vector to sum up to 1? There is a word for that? Do you know the word? Normalization. You normalize the vector. So you take the sum of all those and then divide each position by the sum. It will sum up to 1. And voila, this is exactly what we're doing here in the denominator. So we're summing up all that and then divide the position by sum. And this one by the sum, and this one by the sum. This is what Softmax is doing. So we're turning everything into positive by exponentiation. It's monotonic, so there will be some great properties. It has a good derivative as well. And we just normalize it. So it's a valid probability distribution. Cool. That's it. So the denominator is nonlinear bijection. So yeah, I mean, bijection, so you can turn it back if you want, from real numbers to positive numbers, and the denominator is the normalizing constant to ensure that it sums up to 1. Okay, any questions? Softmax, your friend, learn it. Okay, and then what do we need to know? Okay, so we have Softmax, we have a function. We can plug it into our network. So what we know how to compute the value. What else do we need to compute? There's two things for each function in our network we need to be able to compute. Nothing else. What do we need to do? Yeah, the derivatives, the gradient. How to find the gradient with respect to all the inputs. So what we need to know is how to compute the partial derivative of softmax with respect to each argument xk. Okay, so we need to know how to do that. I think the formula is also kind of pretty. I think we'll do it in the exercise, actually. So it's going to be a somehow nice formula in a similar vein as in softmax, as in sigmoid. Okay, so that's all we need to know. So there is one thing in softmax, which is something called temperature. So we can somehow smooth the softmax by the temperature T. And by the way, if you hear temperature, have you used anything like temperature with anything with LLMs? If you used ChatGPT or something on Hugging Face. So okay, sometimes there is a parameter called temperature, which you can set up. And if you turn the temperature high, the output is going to be quite wild. And if you set a temperature low, the output will be somehow more predictable. This is it. This is what this is what you're tuning. This is the temperature, because what you're doing with temperature is, oops, excuse me, like that. If the temperature is high, so basically everything will be, all the numbers will be much smaller, then the result of the softmax will be more uniform. So, well, this is this would be the without any temperature. So this is probability distribution, and the most probability mass is on category 1. If we have high temperature, then everything will be somehow more uniform. And if you sample from this distribution, well, the probability you get any of those is, well, almost equal. While here, the most probable is this one. If temperature is small, you get a very spiky distribution. So basically, then you would if you sample from this distribution, the chances you're getting only the category 1 is super high. And this is, the same principle is used in large language models for sampling an expert, which we'll be talking about later in this lecture. But the temperature parameter is something actually very simple in the softmax. And you might see it as a, in the papers, oh, we sample with temperature that and that. So the output is kind of, I don't know, wild. Yes?
Very low temperature softmax becomes the next function.
Yeah. So the softmax name is actually, it's wrong. It's not softmax because you're not getting the maximum. So if you're thinking about a maximum of a vector, max of the vector, it's basically the max value. So I don't know, 22, 0, minus 30. The max would be 22. Softmax is giving you like something like that. So it should be something like soft arc max. It's giving you like the position where the argument is the highest. So it's actually a bad name, but it sticks around. For getting the maximum, I think it's soft. Wow, what is it? There is a name, soft log something. So there's a trick how to do the maximum in differentiable way, like approximating the maximum. Well, I don't remember exactly, but softmax is basically getting not the maximum value, but the argument with the maximum. So argmax, basically, in a way. Okay, so this is softmax. Any questions on temperature? So you take a bunch of numbers, exponentiate, and normalize. That's it. Cool. Now, yes.
But then softmax only works for a finite space.
Yeah, sure. Yeah, we have a finite dimensions here. But I actually think that you need to have like finite dimension in your vector space. I mean, why you're asking? Why is it an issue?
Well, because also the problem in gradient descent came to mind, where it can sometimes be stuck in local optima.
Okay.
So, for example, in a maximization case where you can be stuck in any local optima, I was wondering if that could even happen to the argmax, to the softmax function, but since it denotes the position of where the maximum value is, then it can't search through an infinite space.
No, it cannot search in infinite space. But we never talked about infinite spaces. Actually, I'm not a mathematician, but I don't know if you can work with. I mean, there are infinite spaces, dimensional infinites. I'm scared of that. And of course, like in neural networks and in any computer, you have finite spaces. You have a limited vocabulary. You have finite memory. You're more than finite. You have to keep it small to fit the memory of your computer. So everything is finite dimensions, and the dimensions are actually pretty low. I mean, what is the number of parameters of any neural network? Like 70 billions. It's a finite number. So yeah, everything is finite here. So it's finite vector spaces. We keep it simple. Okay. Any other question? Okay, let's move on. So now we know that what is this? What is the problem we want to solve? The problem we want to solve is now we're getting. No, let's have it like that. So our function now is giving us. So we have maybe some function and is giving us a bunch of numbers. I'll just write it as a column vector right now. So we're getting 0.1, 0.8, and 0.1. So this is our prediction y hat, and then our gold label is, for example, 0, 1, 0. So this is the gold label, for example, for the classification, if we had three classes. Now, what we have also, what we need to do is to like, how do we know our prediction is any good? AKA, we need to find a good loss function. Like, how do you know this is close enough? How do you know this prediction, 0.1, 0.8, and 0.1 is good prediction of this gold label? So we need a function. We need somehow to compare, something to compare, right? I mean, you can take a square, you can take a mean square error. Like somebody said this mean square error, yes. Can you do mean square error of these two vectors? Yes, of course you can. So mean square error could be one thing. So you just subtract that and make a square function and sum it up. But as we said, like we're using the cross-entropy thing for many reasons, and we're gonna turn this into also so we have now the binary cross-entropy, we turn it into categorical cross-entropy loss. We call it also negative log likelihood. So there are different names coming maybe from different communities. But anyway, categorical cross-entropy loss. So we have, again, this is our gold standard label, which is a 1 hot, and this is the output of the softmax y hat. And here's a function how we can go deeper and derive this function, but I think I put it into the appendix. So if you're curious how to get this formula, go to the appendix to find out. But this is how we compute the cross-entropy loss. So we're iterating over all these different, let's say, categories. So this is a small number like 3 or 6 or 50,000, whatever, and multiply the value by the logarithm of the value of predicted. If you turn this into, if k is 2, this will turn out into the binary cross-entropy loss. So this is basically a kind of generalization of the binary cross-entropy loss, if you will. So if you remember this, you can always derive the binary cross-entropy, which was minus, I don't know why, p times blah, 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 these two sums basically. So this is the general version of multiple classes. Okay? Yes?
What is done of a really big model? Because I would think like there would be distance measures that would be way more efficient than computing all these logarithms.
Why? Why is logarithm bad?
I mean, I haven't efficiently computed logarithms yet, but I think like squaring and additions, for example, would be way more efficient than logarithms.
So I don't know about efficiency. I mean, it really boils down to what you're running. If you're running on GPU and there's a special instruction for doing logarithms or something very efficient, I would say like, I never actually heard about problems with computing logarithms fast. That's not the issue. The issue is here, that's a good point, to be efficient for softmax, actually efficient softmax. It's interesting. So there's a couple of tricks with softmax. So the one issue with softmax, because you asked, is what is this? The denominator? Well, no, there is one issue, like overflow and underflow. Overflow and underflow. So overflow or underflow, which means if you have big numbers, e to big number will be even big number, and then you just basically you're running out of your precision of your real numbers. So this is an issue, and so this is very naive. If you implement softmax like that, you might be lucky, or you might run into issues of overflow, basically, or underflow, because if you have big numbers here, you're getting into trouble. So there is better implementations of softmax, which ask ChatGPT. Ask ChatGPT, can you implement me softmax in Python? You get an answer, and try to understand it. There's a mathematical proof. Why I'm saying this, I put it into the exam last year, and I said explicitly, like, ask ChatGPT, how to do softmax, because softmax is super easy. Everybody knows this. But you know, if you see the implementation of ChatGPT, it's like, oh, this makes no sense. This is no softmax. And it is a softmax. It's just a simple, you know, if you know a little bit rules of how to do exponentiation, then you'll find like, well, this is, you know, basically a stable implementation of softmax. And then I asked the students like, oh, do you think this is a good implementation of softmax, and why? Why I asked that? Because I mean, we're saying we're gonna use, you know, AI for everything, coding and stuff like that, and we should kind of be able to double check that. So I said, okay, let's put it into test. And you'd be surprised, like everybody failed on that. They say like, no, this is wrong. This is not, and you know, so I'm not gonna put it into the exam this year because, you know, it was a failure, but I'm just saying, yeah, ask ChatGPT to do something which you really think you understand, which is, for example, softmax, and double check it. There's a simple proof, like 3 equations. Okay, and this is, ChatGPT will give you the not underflowing or overflowing version of softmax, which is implemented all the libraries like PyTorch and stuff like that. Okay, cool. Maybe I'll give it into the maybe I'll put it into the exam. Why not? It's no, I'm serious. Like, can you trust your, you know, if you're code completion and you get a softmax and you have no, well, looks like that, I don't know, I'll just take it. So how can you trust it? So, okay. So now what we have so far? We have many things. We have our model, which is a linear projection. We can project it into a probability, 0 or 1, this is binary task, or into a probability distribution over multiple classes. This is what we were just talking about, the categorical, well, not the categorical, I mean, the softmax, you know, turning a vector of numbers into probabilities. So, but we have still a linear map, only just a single linear map, like x times w plus b. So this is a linear map. And there might be problems that are actually not linear in nature, and this function will not solve this. So let's see. So here's an example from a very cool web kind of interface called Playground on playground.tensorflow.org. So I'm just going to explain what I'm doing here, just that it really makes sense. So so this is not a natural language processing. These are just points which are red and blue. And these have, let's say, these are represented as a vector of 2 features, so x and x1, x2. So each point here is x1, x2, so 2 numbers. And naturally, if we display all these data, we see, oh, these are actually, we can distinguish between blue and red just based on their positions on these features. So this problem is we call linearly separable. Okay, so linearly separable. Why? Because we can draw a line between those two and it will separate these 2 classes. So this is something classical from machine learning. Like we have classes and we can draw a line and it's linearly separable. So it's an easy problem. You can solve this very easily. And how we do this here is that we're saying, okay, this is the position in the feature vector, so x1, x2, and I'm running this through. This is just a linear projection. So the problem is classification, and basically what this red part here is saying that everything which falls into this red part is going to be classified as red, and all the points in this part of the space will be classified as blue. So this is what we want. I mean, it looks like a valid assumption for these data points, okay? So any questions to this visualization? Does it make sense? So here we are just basically doing this projection, as I said, like x times w, and maybe there's some bias, maybe not. So, okay, so this is nice, and this is an easy problem. Then let's turn into somehow a little bit more difficult problem. So now we have the space where the blue dots are occupying these 2 parts, and the red dots are occupying these 2 parts. And the first question, is this problem linearly separable? Not. Why? You cannot draw a line to separate these 2 classes. So this is not a linearly separable problem. Okay, but anyway, we tried. I mean, and this basically, this web interface, if you just go there, you can play around, and it just shows you how it's training, and it's like a very nice visualization, by the way. And it tried to find, the classifier which can classify these into two classes. And it fails. It's just basically giving something like, 0.5 loss. What's the loss? I don't know. You can set it up. Say again?
Test loss 0.569.
Yeah, so maybe it's accuracy, maybe it's a loss, doesn't matter. Some sort of a function which should be 0 for perfect match, as it was here, right? I mean, we're perfectly able to separate and train. Here we can't. So that's a problem. And well, no matter what we try here, we cannot solve this problem. So what if, because this is just a simple linear function, what if we stack two functions on top of each other? So let's try. So linear layers. So now, just to see what we have here. So this is our input, and this is our first linear projection. So it will project our input space of these dimensionality into something called D1, so some smaller space. Remember, before we had projection from 50K to 6, and this could be this. Why not? I mean, D1 could be 6, for example. Why not? So projecting from some space to another space, and we have the bias. So this is the first part. And now we're saying, okay, we're taking the second part. We call this output H, because it's also called like hidden vector or hidden layer. We take this vector and project it again to some other space of dimensionality D out. So we project this again to something else. So there are two linear projections. Well, now we don't really know if we train this, if we learn these W's, the parameters, we don't know what's in the hidden layer. I mean, we don't know the semantics of that. Could be something meaningful, couldn't be, who knows? But we are just projecting now two after each other. So the question is, if you do two linear transformation, will it solve our problem or not?
So just transformation, W1, W2 plus D1, W2 plus D2. So we can play out and then we have another linear transformation.
If you do an algebra on that, you will end up with something which is still linear. So two linear transformation as composed functions is still a linear transformation. So stacking these two things together will not solve anything. So it's still linear. Okay, and here's another proof, but just playing around with the example. So you can add here in this playground, you can add this hidden layer. And now actually I said, well, the dimensionality is going to be 4. It could be smaller, it could be bigger, but we have still two input features. So I'm going to say like, yeah, let's try 4. And it's still linear. So it's a still linear function. And as we see again, we didn't learn anything meaningful. So it's still not able to cope with that, of course, because it's still a linear function. Okay, so stacking things together on top of each other is still linear. You cannot solve nonlinear problems with that. But maybe we're onto something. Maybe we're onto something. Maybe we can plug something in somewhere to turn it into nonlinear projection, right? Let's see. So where can we add some nonlinearity here? Can we do something nonlinear here? Something like squeezing something? Yes. Like, you mean here? Between here? So somewhere here we can add some nonlinearity. So we have a vector. And what do you do with the vector? Okay. To transform it to what? It's a bunch of numbers. Yes, you in the back. Oh, you can transform every number in the vector by some nonlinear function. Okay, sounds good to me. What could be this nonlinear function? Do we know any nonlinear function? ReLU. Okay, we haven't talked about ReLU yet, but okay, you know ReLU. Anything we heard about? Yes. We know sigmoid function. Sigmoid function is a nonlinear function. Is it a good one? Who knows? I don't know. Maybe not. Maybe yes. Hyperbolic tangents is also very fancy nonlinear function. Yes, we can use this as well. Yes, in the back. Swish. Oh, geez. I mean, you're doing research now. I mean, we're talking about something, simple now. Okay, yeah. I mean, there's tons of nonlinear functions you can use. We're gonna use something very simple here, but the key question is like where to put it. Well, yeah, of course, we're gonna put it here in the middle. Why? Because we want to squeeze the, so now we're back to the analogy like what nonlinear function means. It's basically linear projection is lines will be lines. We had this example like projecting 3D to 2D, lines will be lines or dots in the worst case. If you squeeze it through some nonlinearity, you're basically going to wrap the space. This is how I kind of understand it. So you're going to turn things which are lines into things which are not lines. Could be some, well, not polynomial, something like very kind of squeezed or wrapped. You're wrapping the space by these nonlinearities. This will help us to transfer the problem, which is not linearly separable in the original space. We're talking about representations. We're projecting into another space, another representation. And in this representation, things are kind of wrapped or kind of turn around in the space, which may make them, after another projection, linearly separable. Right? I mean, we're turning the space into something like, can I turn this around? Then, if I cut a line in the new space, I can classify these things because it's becoming linearly separable somewhere here. Somewhere here, the problem will be already linearly separable because of the nonlinear transformation in this in-between space. This is how I think about deep learning basically in general. Like you turn things which are somehow complex and you learn the projection to spaces where things are getting easier to be separable linearly. Because at the end of the day, there is a linear classifier. Like this one is the linear function. And after that, everything should be decidable. Like everything should be separable. But these nonlinearities in the middle are making things really interesting. So, who said ReLU? Okay, what is ReLU? All negative gets 0. Okay, is it something like that? Okay, I guess you were right. So, ReLU is very, very cool. I mean, tangents, hyperbolicons, cool one. Yeah, it's been used in deep learning for ages. Sigmoid, yes. What was the other? Swish, GELU, whatever. All these kind of fancy techniques. Yeah, sure. But we have something like super simple, which means it's a linear function for all the positive numbers. So it's basically identity. And then for all numbers which are negative, we just turn it into 0. It's very crude, brutal, nonlinear function. Because lines won't be lines. Like everything which is negative will just turn 0. And everything here will be cool. So this is ReLU, your new friend. It's very easy to implement. It's just max 0 or the value. Yes? Okay, cool. Now we're talking about gradients because every function, we know how to compute the output, but how to compute the derivative. So what's the derivative of ReLU, by the way? What is the ReLU with respect to its input? So it's 0 and 1. Awesome. Well, this is the nicest derivative you can ever have. Because it tells you like whatever because you're multiplying chain rule. You're multiplying, remember the computational graph, we're multiplying all these derivatives together and the chain is quite long. And you're multiplying things. If you multiply a thing by 1, awesome. You don't lose precision, never. So this is great. Derivative of 1 is awesome because then you can focus on these things which really matter, like the inner functions, not the activation. The 0 is an issue. Like, so what are we gonna do with that? We can change it. So there are some alternatives of ReLU saying, for example, it's not gonna be just 0. It's gonna be something like very, very, very small decay, something like that. Is it the swish thing or not? Leaky, this is leaky ReLU. Okay, so there's fancy words and fancy names for all these things. So leaky ReLU, and you can have jello, which is something like a knee here and then goes 0 and stuff like that. Well, so there are alternatives, but as a rule of thumb, just go with ReLU first. You can't go any wrong. Because why 0 is actually maybe not a problem. Because if the derivative is 0, it's saying whatever is coming in to this function plays no role. So it's basically making the neurons which are coming in, so the functions, kind of dead. So they won't be updated because they don't matter for the output. It's a feature and a bug at the same time. Well, it's not a bug, it's a feature. So this comes from, I guess the theory behind that is not a theory. The intuition behind that is like neurons, most of the neurons are dead, are 0. And some of them are excited, like positive values. And this is what it's trying to do. Like some of them, like most of them could be zeroed out, and some of them are just activated. I think this is coming from the field of like neuroscience maybe as well. And maybe there's no theory whatsoever. Somebody just came up with this and said, like, yeah, this is awesome and it works. So empirically this works. So ReLU, okay? Any questions to ReLU? Okay, so you should remember this. Now, will it solve our problem of non-linearity? Yeah, of course. So ReLU. Now I just use 3 neurons, and now you see like it's turning our problem into, it's basically, well, now it's not lines here. It's projecting back to the original space, but in the outer space there will be a linear separation. So we can solve this XOR problem with ReLU, or with it's one function, the second function, and there's non-linearity in between. So we can solve this problem now. Okay? Does it make sense? Yeah. And basically, how do we, where do we get these W's from? Well, we have to train this. These are trainable parameters. We have to train them on the problem. But the rest is just functions. And by learning good parameters, good projections, we're able to solve these problems, which is not linearly separable in the original space, but we learn some intermediate representation which make it linearly separable at the end.
Somehow you away some part of the image and then it was video on the other part.
So these are 2 questions, like why ReLU is solving the problem, which is, I guess, theory of machine learning, which I have no idea of. So, there is a mathematical proof. I'm pretty sure like, why ReLU can solve some problems. Why is it solved in this particular case? Well, it just learned, I don't know. So what was the other part of the question? Well, it's turning the space into non-linear space in a way. This is the intuition. Like how exactly it will work for the case, it depends on the case. But I would just go there and change this into tang H or sigmoid, and you see how it will change the space here. So some of these things so ReLU is still somehow, you see like the sharp edges and lines. So this seems like this is a ReLU. If you turn this into tangents hyperbolicus, you will get something like maybe this, some more like curvy shapes and stuff like that. So ReLU is kind of crude, with these still linear and non-linear at the same time. So this is how I understand it. Yes? Maybe, yeah. Yeah, maybe. It's really hard to imagine things in high-dimensional space and non-linearity. It's hard. So I don't have a good intuition that I could kind of explain in a way. I'm sorry about it. But I really suggest like go here and play around with that. It's a really cool like web-based thing. So is XOR relevant in NLP? That's a good question. And I have a very superficial example here, but why not? So let's say we have a movie reviews problem, binary. So we have a vocabulary of size 3. So this should be like 3-dimensional space, and the binary features have values 0 and 1. So if something is not good, it's here, and if it's something not bad, it's here, and if it's something good, it's here. And so can you see the 3D space here in this picture on the left? Okay, so now, and I just draw this plane because I'm turning this plane into like this view. So I'm looking on this as a plane from the above, which basically it's just a simple projection of not good. So basically looking this on the side. So now these are in 4 corners, these 4 documents, these 4 features. And I want to do binary sentiment classification. Can I run a linear? Is it linearly separable? No, because what I want is that this is one class and this is another class. Like good and not bad are positive and bad and not good are negative. Simple XOR, so exclusive OR. Either or, not both. It's superficial, but I didn't. If you think of better example in NLP, like let me know. This is the best I could come up with, which is like simple to visualize. But non-linearity is a problem in NLP because you have nonlinear relations between features. Okay? Cool. So let's move on. So welcome to, finally, feed-forward network. So what we built so far is or it's also called multilayer perceptron, and it has a long history until the 1960s. Well, anyway, so we can see this as stacked functions together. And this, most of the time, this is a linear projection followed by a nonlinear function. So we have the first, we can call this as a, I don't know, input layer or the first layer. I mean, layers are, depending like how you look at your layers, is it a thing, is it a function or is it the output? What exactly is a layer? So I don't like this terminology because it's confusing. But if you look at this as a functions, then it's really clear. Like, oh, okay, this is a linear function, this is a nonlinear function, there's another linear function, there's another nonlinear function. So if I see it as a computational graph of functions, to me it's very unambiguous, and so I can reason about things much clearly. But what do you see typically in all the literature on deep learning? Oh, there's our layers, and there's input layer, hidden layer, output layer. And most of the time, the layers is something like that. So it's a projection followed by nonlinearity. This is something called a layer. So there's, I guess, this input layer. Then this would be the output layer. I don't know. Is it the output layer? I'm always confused. Why is it output layer? Anyway. Yes. No. Yeah, okay. Would this be a single node? It's then most of the time, yes, because it's a function, and it could be a single node because you can put the parameters into the node. It's a matter of implementation. What we are implementing in our time ladder framework is that we keep the parameters out of this function as a children of this node to make it very explicit. What you see in PyTorch, basically, these are packed into the node implementation or layer. There's actually a layer implementation, which is kind of even more, taking multiple inputs, multiple outputs. Yes, you had a question. Yeah. Like here? Well, there's another one, which is the softmax or another nonlinearity. So you basically put some nonlinear function after each linear function, typically. So this is a linear function, and there's some nonlinearity. Typically, what you see is also something like, okay, here's an input, here's my nonlinear function, which is, let's say, sigmoid x times w plus b. So this is just a single box. And then there's another layer and another layer same as this. So there's some linear projection followed by some nonlinearity in every layer. It's a matter of detail. I mean, now this is very detailed. Like I put the parameters outside of these boxes. Typically, you have them as a part of these boxes. So it's really like how you want to depict your network and how much detail you're having in there. At the end of the day, it's this function. This is the actual like mathematical description of the function. how you want to show it in a computational graph or layers or network, it's a matter of design choice. Does it answer your question? Sort of. Okay, cool. Okay, so this is the feed forward, and then we have one layer, and of course we can repeat this layer multiple times here. Not the same one, like different parameters, but we can stack these nonlinearities like one after each other. So the layers could be, how many layers deep could the network be? Well, it could be very deep, yeah? N? Yeah, it could be N. It could be very deep. It could be 10 layers deep, 20 layers deep, 100 layers deep. I don't know if actually like if there's some functional like super deep network. Well, actually there are. I mean, why not? Like the transformers are not really deep, but they're just huge. Recurrent networks are maybe deep. So you can stack them together. It's basically combining functions after each other, after linear projection and non-linearity. So feed-forward network. Okay, any questions? Cool. Yes?
As an example, I translate the neural network was, if I'm not wrong, two hidden layers with 8 layers embedded within.
How do you know?
I saw the research paper that described how Google Translate was.
So there, okay, so Google Translate, so okay, there might have been some information about Google Translate maybe 15 years back, maybe 10 years back.
Paper was from 2006. Well, I think in 2016.
I'm pretty sure in 2012, 13, 14, 15, 16, they turned completely neural and they turn into some like recurrent networks, LSTM stuff, which is something conceptually quite different than feed-forward network. So I'm pretty sure they use something like LSTMs for machine translation before turning into transformers like recently. So yeah, but LSTMs is conceptually a little bit different than just. I mean, everything is feed-forward network in a way. You have inputs and layers of depth, and there's some output layer. We will be talking about recurrent networks in maybe 2 weeks for machine translation, actually, or text generation. So, but this is the basic building block of most of the machine learning or the deep learning things today. So, yeah, let's move on. Language modeling. Who of you took the Intro to AI lecture this year? Okay. Who of you never heard of language modeling before? Okay, good. So for those of you who heard it, I'm gonna skip. You can just pause out, and because you've heard this. So the goal of language modeling is to assign a probability to sentences in languages. So example, what is the probability of seeing the sentence, "The lazy dog barked loudly"? This is the language modeling task, like in a classical perspective. What is the probability of this sentence in a language? What is the probability of this sentence in a language? What is the probability of this sentence in English?
I know, but might use very many training books, so maybe actually.
So the answer is who knows? Like, how do you decide? Like, how do you know how do you know there's a probability of sentence in a language in the first place? Like, how do you? Can you know the probability? Not really, because you don't control the generation process. I mean, if you control the random experiment and you can run your, I don't know, like simulator of producing random things, then you know the probabilities exactly. In language, like you don't know. So yeah. So the first question, like, is it an objective goal or not? Is there a truth? And the answer is, well, who knows? Maybe not. Maybe we don't know. So what we are going to do instead is like we need to estimate the probability. Somehow like make the best guess. What is the best guess, the probability of the sentence in the language? And you're saying very low. Well, I would say it depends what you compare to. So if you compare the probability of sentence "the lazy dog barked loudly" to the probability of the dog slept, or the dog was sleeping, I would say like the dog was sleeping is much highly probable than the other way. Okay, but it depends. If we have this probability of the whole sentence, we can turn into probability of what is the probability of seeing the word bark after seeing the lazy dog. So we can turn a joint probability into conditional probability. And we can ask, basically using the same probabilities to get these. So formally, we have a sequence of words, W1 to N, so W1, W2, and so on. And we want to estimate what is the probability of this joint distribution. So we are actually misusing notation quite a lot here. So basically what we are trying to do is what is the probability of the first random variable, first word being W1, this should be 2, excuse me, the W2 being W2 and Wn being this actual kind of representation, this actual word. So we have a set of random variables for the first word, second word, third word, and so on. And we have a joint probability distribution of these variables. And we are interested, what is the joint probability distribution of seeing exactly these words? What we actually write is just, simplifying that without actually naming these random variables. So just, don't be confused by that. So we have a joint probability distribution, and we can factorize the joint probability into a product. So if you know the rules of conditional probability, and yeah, that's it. Conditional probability, how to compute conditional probability, then you know how to factorize joint probability distribution into a product of conditional probability distribution. If this doesn't tell anything to you, just go to the appendix and there is some refresher on probability. So just you can do it on your own, to understand this more in detail or just to refresh probabilities. So one factorization is actually quite useful, which is left to right. So we're gonna factorize this into product of conditional probabilities, which is saying, so the S, what could be this S? We just introduced something very awkward here, some symbol S. What could that be? Maybe sentence? Not at all. Not at all. So we call it a start symbol. So S is like a start symbol, which is something artificially added. So we're saying our sentence is maybe like start symbol and then the dog and so on. And we're saying, oh, the joint probability is going to be product of probability of seeing the first word after start, then times probability of seeing the second word, being, for example, dog after seeing start and the first word, and so on, so on. Okay, so this is basically just a factorization of the joint probability. If you know the rules of joint probability and conditional probability, this is just it, just using the definition. Okay, why this is interesting and important? Yeah, so far not really, because there is no easy way. Like it doesn't make life any easier by having this kind of product as compared to just the full probability. So we have to simplify things, because despite this factorization, the last term of this factorization is still like super large and have all the previous, so this still depends on all the previous words of the sequence. So we're gonna simplify that and we're gonna say, you know what? Yeah, maybe we just gonna always take not all of those, but we make a cut here. And we will just look into the history of maybe a couple of previous words to estimate the probability of the next word. Is it a meaningful assumption? Sometimes yes, sometimes not. It's a local one, but it will make our life much easier. So it's called the Markov assumption. I think like Markov assumption is used like in all different places where you say my state is depending just on the previous state, something like that. And maybe in physics, Markov assumption, probably random processes. I don't know. So we're gonna make an approximation and saying like, okay, the whole, the conditional probability based on the whole sequence is gonna be something like the conditional probability given just the k previous words, something like that. So last k words is more important, and we just forget what was at the beginning. Is it a meaningful assumption? Yeah, make a lot of sense. I mean, sometimes for predicting the next word, you just need to know like the last 5 words. In many cases. In all cases, well, not at all, of course not. Sometimes you need a full sentence or the full document or the whole world to predict the next word. So the context matters. Anyway, The question is, how do we estimate this? How do we learn these probabilities? Because we know we don't know them. We have to somehow estimate them. So how do you estimate the joint probability of a word given previous words? Is there a fancy technique for that? Yes. Okay, so we need a large text sample. Okay, so let's say the internet. Okay, can we take the internet? How do you take the internet? I mean, it's I just say like, let's take the internet and train it. Like, can you take the internet? How do you take the internet? Do you want to crawl it? Have you tried to crawl the internet? Yes. Okay, I did it too. So I'm gonna never do it again. Because my university almost got banned from Springer. Yeah, because I did it on the university clusters and well, whatever. Anyway, so don't crawl the internet because somebody did it for you. There is a thing called Common Crawl, and it's like US-based nonprofit organization which is crawling the internet every month. And all these large language models, like most of them, are based on some common crawl data. So they crawl the internet, maybe some filtering. You have to do the filtering, and you have billions of trillions of tokens or text. So we have the internet. Then what? Wow. Okay. Very fancy word. So what is maximum likelihood estimation? What is it?
Depending on the last pair words.
So you're counting some words, and
The words in the whole text figure.
something like that. So maximum likelihood. So it's very fancy word for counting and dividing. You just count and divide. This is how you compute your conditional probability. And you're counting the sequence, including the last word, which you want to kind of find a joint probability, conditional probability, and divide by the number of times you see the previous context. Counting and dividing, maximum likelihood estimation, a very fancy word. Okay, this is it. This is how you build your language model. You take the internet and you count and divide. This is not how you build ChatGPT, because this will have some issues. What will be the issues of this classical language model? What issues can you run into? Well, what if you never, well, okay, what if, no, not what if. The problem will be, if your context is large, well, you will end up with many parameters. Okay, great. And then for many combinations of words, your probability will be 0, because you never see the combination of these words together, because there are so many words, so many sentences, and it will be sparse. So you will run into issues that most of these probabilities will be just 0. And 0 probability is a bad thing, because if you remember, we're multiplying these conditional probabilities together. So if you multiply something with 0, you will end up with 0 probability. Although the sequence doesn't have a 0 probability, it has some small probabilities. So this is the first problem. And of course, the longer the context, the bigger the issue of sparsity, and then it turned out like this doesn't really work. So these are classical language models like n-gram language models, and the n typically would be 3 to 5, maximum 6 words, I would say. Maybe like the largest n-gram model ever was maybe 6-7 gram models, 2007 from Google by NLP paper. Very huge, very large, but there is some limited context you can cram into this model. So this is the issue. Yeah. Yes. Yeah, but you're still running into the issues of sparsity, because if you add, it is basically exponential. So if you increase the context here, the k, just by 1, it exponentially increases the number of samples you need to see in order to fill these probabilities, right? If you have 50,000 words, 100,000 words. So you need to have table. Basically, this is filling a table with numbers. You need to have table of size 100,000 times 100,000 times 100,000 for a 3 gram. All these probabilities you need to estimate, right? Because these will be this is one of 50 or 100K, and each of these words in the previous context is again like each word in the vocabulary. So you need, for all the pairs of words, you need to know how to compute their probability. You need to know how to compute the probability of sequence, the lazy cat barked loudly. What is the probability of this sentence? And you would say like, I have 0 because I've never seen this sentence before, or these 5 grams. So the space of possible solutions, not solutions, like the possible parameters you need to estimate is growing exponentially by each context size, right? Because I mean, you really need to go through all these words to get these probabilities. You're not limiting yourself to just a selected, I mean, you can make the vocabulary smaller, but it doesn't solve the problem. Does it make sense? Okay, cool. Where are we? Okay, so this is good. Counting, dividing, it will get you far, but not far enough. So how do you know that your model is working well? How do you evaluate your language model? So there's a thing called perplexity. So we have the trained language model tells us the probability of sentence, which is sentence S, and the probability of S. So the model, if it's trained or estimated, it can tell us the probability. Okay, this is cool. So we can have n sentences in some test corpus. So we train it on the internet and keep part of the internet as a test data, right? Training test data, similar, we talked about this before. So n sentences in the test corpus, and each of them has a uniform probability of appearing 1 over n. So these all sentences in the test corpus are equally likely. Then the cross-entropy of our model. Oh, cross-entropy. We've seen this before. Okay, so we are always in the cross-entropy kind of realm, like cross-entropy loss, computation of cross-entropy of probability. So there is some underlying foundation why this is interesting or important. So we compute the cross-entropy by taking the probability of seeing in the test data times the log of the model predicting this. And after doing a little bit of math, we turn log 1 over something into minus log, so it will be we just move this out. Okay, so it will be 1 over n times log this, and now we turn this into minus log and get rid of this fraction. So this is what we're getting. Okay, and then we make the perplexity of the language model will be 2 power cross entropy. So 2 to the power of this cross entropy is the perplexity. So the lowest perplexity would be, I guess, 1, because this could be only 0 maximum. Like this will be, the minimum will be 0. So the lower, the better. What I'm saying, the lower the perplexity of the model has, the better it can kind of estimate the probabilities of sentences in a language. And this is how we measure it. We train it on some training data and test it on some sentences in our test data. And if the model is getting good predictions, basically, of these sentences, the lower perplexity, perplexity means like, how much confused the model is. The lower, the better. Okay, so you can compare language models, including like ChatGPT or like any transform models. Underlying mechanisms, you can ask them for probabilities of sequences, and they should have low perplexities. If the model is better, the lower perplexity is better. Yes? So the loss, so what is a loss? What do you mean loss? Okay, yeah, this is interesting. Yeah, that's right. Okay, so when we're talking about loss, you mean basically, when you say like the loss, I'm thinking of a loss for training, so the training loss. So I'm having training data set, I'm trying to minimize the loss by whatever, some minimizing by propagation, whatever. In these estimations of these, this counting and dividing, we don't have any loss in there. So that's why we just use, the test data to predict our perplexity. So you can compare in the same metric, regardless of how you train your model, you can compare them, you can compare classical language models on perplexity with narrow language models on perplexity. That's maybe the answer. Okay, so this is the cross entropy, the perplexity of a language model. So what are the shortcomings? I mean, we talk about it, like Ingram language models. If you have very long range dependency, then if the dependency is like 10 positions, you need to know something from the very beginning in order to predict the word at the end. And there's 10 tokens in between. What could be the example? Something with grammar. Okay.
Then there's like something in the middle of the sentence, and then the original sentence continues.
Yeah, maybe, or maybe anything in German with the past tense, like ich hab blah 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 gemacht. Maybe there's some dependencies. Well, whatever. You can have like long dependencies in grammar or anything like content as well. So this won't work. This will fail. And of course, if you observe black car and blue car, then if you see red car, you don't know anything about red car because black and these are like different tokens in the vocabulary, and you cannot learn one from the other. So this is kind of hard. Okay, so let me see what can we do for now. Maybe we'll stop here. Yeah, sorry, you had a question.
Solve that problem?
Implementing what? Say again. Implementing, I didn't understand. Cutoff length for sentences.
Some language models, they set a cutoff length for the input sentences to.
Okay, yeah, you can solve it in many different ways by saying I'm not accepting anything longer than 5 words. Then you can use standard language models. But is it a good feature? Maybe. Sometimes maybe it can work. Sometimes maybe it's a bad, so there could be better solutions. Okay, so I would say let's stop it for today, and we'll be talking about other stuff next week. And today, yeah, I'll see you the exercise. It might. Let me just stop sharing here. Sorry, and stop recording.